I'm pleased to have with us here Professor Gottsman. I've worked with... What? All right. I've worked with Professor Gottsman in the past, and I'm glad that he's here with us to talk about some of the last interesting stuff he's been working on in the Technion.
Thank you.
Go ahead.
So it's my first visit to Google. I'm very pleased to be here. Thank you for coming to hear me. So I'll talk about a problem which arises in computer graphics, which is what I do for a living, basically. And the formal title of my talk is multi-texture mapping using the GPU. So I hope it'll be of interest to people who are working on computer graphics, more specifically the Google Earth and Maps groups. I think it will. So typically what is done in computer graphics in visualizing urban scenes, and when I say urban scenes, I mean scenes are basically of buildings, of streets, and things like that, as opposed to, let's say, terrain rendering, which is a slightly different application. So typically what is done, and here you see an example of a small piece of an urban scene in Germany somewhere. I'll show you a demo here. So this is your urban scene, and it's basically a synthetic urban scene, meaning this is not a real photograph or anything like that. It's basically three-dimensional geometry overlaid with texture maps. That's all we have here. This is a VRML file which describes the scene, meaning the three-dimensional shapes of the houses over here, and you can see the three-dimensional shapes, actually the polygons here in wireframe. So it's pretty modest in terms of the content, the geometric content. And most of the content is basically the texture maps which are pasted on the fronts of those buildings. That's what makes it really interesting. I'll put it back. That's what it looks like. So what we have here is the geometry, and we have the texture maps pasted on top. And I can show you what the individual texture maps look like. Oops. So here's one, right? So this texture map belongs, I guess, to, I don't know, I can't really see it right now. Here's another texture map. It's a piece of some facade. Another texture map, and so on. So there's basically a bunch of images, which is what we call texture maps. Each one of these individual images is a piece of the front of the building, and basically it's pasted onto that geometry, and it's fixed, meaning that specific piece of geometry will have this specific texture map forever and ever until I change the definitions. So basically when I'm looking at the image you see over here, and I apologize for those of you who do this every day, I'm probably not telling you anything new, but for those of you who haven't really seen it or worked with it very much, this is basically the introduction. So you have these texture maps which are pasted on the fronts of these buildings, and if you want to walk or fly through the scene, as you want to do with some virtual reality or some simulation program, basically what you do is you'd have your virtual camera and you'd walk through it much in the same way as I'm doing right now, just using the mouse, and you could see from every given viewpoint, you could see that geometry pasted with that specific texture map which was associated with it, and you'd get the result that you see over here. Now this is the traditional and totally standard way of doing computer graphics using texture mapping. In this case, it's just the VRML. So let me get rid of that. So here's the same type of application. This is a scene from Israel. This is where I'm from. This is the Israel Parliament, the Knesset. And you can see it from various different angles, right? It's the same building. You see the building here from the top and from a different angle and from all different angles. And basically what you do is you take these photographs. If you want to build a scene like we saw before, you take this bunch of photographs and you'd cut out from each one of the photographs, you'd cut out a piece which you think would be best used as a texture map, and you'd use it to texture map the geometry. This is the geometry over here. I actually pulled this off Google Earth. It happened to be there. So I didn't invent this and I didn't build it myself. I just went into Google Earth and I happened to see the Knesset. Somebody had modeled it, so I said, oh, that's a nice, good example. And then I went and I looked for pictures, because these photographs weren't necessarily related to this. I looked for pictures of the Knesset, and I found these pictures, and I said if I'd really want to build a fully textured model of this building, these pictures would probably be a good source to cut the texture maps out of. Right? So we'd cut a piece out of here. Right, so here are two pieces which I might want to cut out. This piece over here on the top on the left, and over here the roof. right, the roof of the building. So I'd basically be able to, if I really wanted to, I could basically cut out bits and pieces of these different photographs and use them as texture maps like the ones you saw in the previous example and build this nice textured model of this particular building. And then I'd put it in Google Earth or put it in anywhere, basically, in any VRML or visualization type of scenario or application, and I'd be able to do exactly what you saw previously. But this is a pain in the neck. Why is that? It requires you to actually go out and photograph this building from all different angles, and then to painstakingly go and look for the individual texture maps for each one of the polygons in the geometry, right? So the geometry is what you want to paste it on, so you have to find the texture map for each piece, for each polygon in the scene. So you might want to cut out a piece from here, and a piece from there, and a piece from there, but it requires a lot of work, manual labor, so to speak, going in there, cutting out the pieces, making sure they fit to each one of the different polygons, and then putting it all together into one file, and then you might have the result that you saw earlier. What I'm going to talk about today is an alternative to this method of doing things, this way of doing things. This is what I call, the traditional way of doing things is called a single texture scenario. Because once I pull out or cut out this piece of the texture over there and I associate it with this polygon over here, it's going to live there forever and ever, and it's never going to change. That piece of texture is always going to be displayed or rendered together with this polygon, no matter which angle, basically, I look at the structure from. So the alternative, and this is basically the topic of my talk today, is the multi-texture scenario. The multi-texture scenario means the following. In a nutshell, before I tell you the details, every polygon, or in fact every pixel in the end of the rendered image, is going to get its texture content, meaning the color, basically, coming from a texture which is determined on the fly as it's being rendered. And it's not going to be fixed ahead of time. And the idea is to choose the best possible pixel at every given point in time for that particular rendering of the image. And that way hopefully we'll get a better result. So how do we do this in practice? In practice, you have your scene, for example, this little village over here, and you take a number of photographs from a number of a small number of angles, let's say 6, 7, 8, or 10 angles, and hopefully you're more or less covering the scene. You see more or less in the union of those 10 photographs, you see more or less everything that there is to see inside the scene over here. Okay, so now you have 10 or a small number of photographs, and if I want to fly through this, I'm going to have to produce new images from different viewpoints which are not necessarily one of those 10 photographs, right? So the question is, how am I able to take those 10 photographs and then use them on the fly together with the geometry of the scene to be able to produce a new or what we call a novel view of the scene from any particular viewpoint which does not necessarily coincide with one of the photographs. So I'm not the first person to think of this particular idea and to work on it. There is work, and it dates back to 1996. Paul Debevec at Berkeley did some work which was relevant or related to this. At some point it was called image-based rendering, although it's not exactly that, as I'll tell you about in a moment. And there is some other work which has been done over time. These are the main references. The problem with the work done was that none of them actually demonstrated real-time performance. So basically, even though in principle the idea is the same idea that I described over here, there is no real interactive or real-time system which allows you to fly through the data and do the type of stuff that I'm trying to demonstrate here. So that's basically what I'm going to tell you about now, how to do this type of stuff and get real-time performance, which is what you really need if you want to do it properly in a real application. Okay. So as I said before, the input is some of the input is a number of photographs of a scene. So here's a village from Israel. And what we're going to do is we're going to photograph this village from a number of different angles. Here's just one angle. It's been photographed from the air. And we're going to combine this with a three-dimensional model of the scene and produce the new images that I'd like to have from any different angle based on just a small number of photographs in the 3D model. So one input is the oblique images. And the second input is the actual 3D model. 3D model, I mean the geometry of the buildings inside that scene. And the first thing that we have to do is for every one of our photographs, we have to be able to register it correctly register the photograph with the model. So basically that means to be able to determine where the camera was when it took that photograph. The moment I know where the camera was when it took that photograph in the coordinate space of the 3D model, then I can actually align it in the way you see over here, and I can get a good fit between the 3D model and the photograph itself. So if I wasn't trying to do what I am trying to do, and I'd go back to the previous scenario of using single textures per polygon, what I then might attempt to do is to say, well, hey, this is pretty good. Let's just cut out little pieces of this photograph and stick them onto the polygons which happen to be visible over here. And that would be a single texture. We'd be back to the single texture per polygon type of scenario. And that I could actually do, but I'm not going to do that. What I want to do right now is to align the photograph, because that would be a lot of work. What I want to do right now is to align the photograph, to register it with a 3D model. And this I'll do for each of the different photographs that I've taken, 10 or 6 or small number of photographs. I need to do that because I need to have some sort of way of determining how the two sources of data actually correspond, what the connection is between the two. So if your camera has a navigational device on it, meaning it has 6 degrees of freedom, it tells you where it is in space and where it's looking as it takes the picture, then doing this is relatively simple. Right? You just have to more or less figure out the calibration between the two coordinate spaces, but once you have that, you're basically done. You don't have to fiddle around and try and match it to in a complicated way, which is what you would have to do if you don't have any information at all about the relationship between the camera and the angle from which the photograph was taken and the 3D coordinate space in which you have your model. So if your camera is equipped with a correct navigational device, this is very simple. So I'd like to draw your attention to this area over here. I hope you can see it from where you're sitting. There is a building there. It's actually a mosque, and it has a minaret, a little tower. Right? It's over here. See the minaret? It's this vertical thing over here. And it hasn't been modeled correctly. Modeled correctly meaning I don't have the geometry of that minaret inside. The blue lines is the geometry. And somehow when they built this 3D model, either they didn't know about or they didn't care about the minaret of the mosque, and therefore it's not in the 3D geometric data set. So something bad is going to happen there. That's just all I wanted to tell you. And if you try and look at the same scene from a different angle using just the photograph without the 3D model, it's going to look very flat, of course. Because if you have no 3D model, you don't know what's standing up in the air and what really is flat. And all you can do is basically just move this flat thing around in space and look at it from various angles. This is what you're going to get, which is obviously no good. If you use the 3D model and you look at it from a different angle, the buildings suddenly start to grow and to appear the way they should. And this is what a novel view, meaning a view from a different angle, not from the angle from which the photograph was taken, will look if I combine the 3D information with the texture meaning that photograph, and look at it from a slightly different angle. So basically my objective is to be able to produce these type of images all the time on the fly in real time as I fly through the data and change the camera, the virtual camera parameters. So again, this is the difference between the two. This is if you don't use the 3D, you get this flat plate. If you do use the 3D, you get a real nice, something which looks like the way you'd expect it to look. But even though we do have correct 3D here, we do not have the correct 3D of that minaret of the mosque. So if you look at the result over here, the minaret is basically gone. This is the mosque, and there is no minaret because it wasn't modeled correctly. It didn't feature in the 3D data set, so obviously it's not going to be here as well. Right, so here's another angle. And this is what it looks like. This is the same mosque in the red circle. And this is what it looks like again without the 3D information. It's basically just a flat thing looked at from a different angle, and you can see that the buildings are looking they look like they're falling over, right? Whereas if you put in the 3D information, it looks better. The buildings no longer look as though they're falling all over the place, but the minaret is still not really where it should be. Basically, it itself is flattened out instead of standing up vertically in the air. So that's something you have to live with if you do not have that information inside your model. I just wanted to point that out. It's something you have to be careful about. So we'll take a little break here, and I want to tell you about something related. It's a little bit amusing, entertaining. There is an artist, a British artist, called Julian Beeves, who draws these type of pictures. This is sidewalk art, meaning this is a picture he's drawn with chalk on a sidewalk, And if you look at it from a specific angle, it looks pretty real. It looks as though you have the correct perspective, and it looks as though it is a true three-dimensional object. So this is one of the examples of a drawing that he drew on a sidewalk. And if you look at it from this particular angle, it looks like this woman is inside this pool and her leg is up in the air and so on. In fact, the drawing is that. That is the actual drawing on the sidewalk. And if you look at it from the incorrect angle or from a different angle, the whole thing just flattens out and you don't see anything, anything which looks like anything. And basically, this is the same type of artifact that you saw in the previous examples that I showed, where you were looking at that flat thing from the wrong angle. Right? So if you don't have the three-dimensional information there, which is equivalent to looking at it here from the correct angle, you're going to get all sorts of crazy things. You can see, this is just an amusing point, look at the length of the leg. Right? Over there it looks like, or her foot. Over there it looks like it's very short, the correct proportions of a foot, but in fact, when he drew it on the sidewalk, it's a very, very long thing, and it's the perspective foreshortening which actually makes it look. So I don't know why we have English United States over here. I apologize for that. Anyway, this is one example of his work, and here's another one. This is in Scotland somewhere. There's a globe, and it looks like there's a guy standing on top of the globe there in the middle of the street, right? And in fact, this is in reality what it is. Right? So it's just a picture drawn on the sidewalk. When you look at it from an arbitrary angle, it doesn't look like anything special. It's quite flat. But when you look at it from that particular angle, you get the correct perspective, and it looks like the real thing, including all the 3D and including all the special effects, like the guy standing on top of it. So for those of you who don't know about this guy's work, I encourage you to look for some of it. There's a whole bunch of these drawings. There's maybe about 20 that you can pull off the internet, and they're quite amusing, and they all show this type of effect. Some of them are quite sophisticated in terms of the three-dimensionality that it projects to the viewer from the correct angle. Sorry? It's just his head, and he imagines how things should look from a very specific angle, and he just draws it like that. I don't think he uses any specific mathematical or tools or machines to help him. He just figures it out in his head. Yeah, he's pretty talented, and it's his lifetime work. He does things like this. Okay, so back to business. What I want to do in multi-texture mapping is not to use one specific texture map for every polygon of the scene and to cut it out from some photograph and associate it with that polygon ahead of time and then use it during the rendering. I want to do something completely different. I want to just use a number of photographs and not necessarily cut out bits and pieces of the photographs in order to align them with polygons. And in fact, I want to get rid of the whole polygon concept. I do not want to use texture maps per polygon. I want to do the rendering per pixel. In other words, when I produce an image as I'm flying through it, I'd like each individual pixel of that image to get its color from one of the photographs, and not necessarily the same photograph at every point in time. The identity of the photograph from which I'll pull out the pixel which I'm going to use to render it is going to change all the time depending on the viewing parameters. So it's multi-texture mapping, because I'm using a number of textures simultaneously, so to speak. And the specific texture from which I pull out the relevant text cells or texture elements is going to depend on the viewer. So basically, I can optimize it on the fly to get the best possible result, depending on a variety of parameters, which I'll talk about in a moment. The two most important ones being A, visibility. Because remember that in not every photograph is going to give me a coverage of the entire scene. A building might be visible in 2 of the 10 photographs and invisible or occluded in the other 8. So that's something I have to be careful about. And I want to take of course, I want to take the texture pixels only from the photographs which are relevant, those in which the building is visible. And on top of that, I want to use, among the ones which are visible, I want to use the best possible photograph or some combination of the best possible photographs, the one with the highest resolution, the one with the best angle which matches the particular viewing angle that I'm looking at right now, and so on. And all this has to be done in real time. So basically I have to make all these decisions as to which pixel to pull out of which photograph and actually do the texturing operation. All this has to be done very, very quickly in order to produce the real-time rate of image generation, which I need to be able to fly through this. Towards the end, I'll show you a demonstration. And you'll see this actually for real running. Well, it's actually going to be a movie, but it was taped off the screen. And in order to be able to get real-time performance, we have to use GPU programming, because for 2 reasons. One is the traditional graphics pipeline allows only texturing of polygons, which is the old way of doing things. And if I want to do the texturing on a per pixel basis, I have to somehow change things in the graphics pipeline. And the way modern graphics hardware allows you to change things or to intervene in the graphics pipeline is using the GPU. The GPU allows you to program using a shader, Fragment, and Vertex shaders, and to actually get into the pipeline and do things differently than what it would be doing if you weren't helping it or changing it. So that's we're able to do using Vertex and shaders and Fragment shaders, and the shading language that we use is GLSL. There's a number of shading languages out there that you could use. This is probably one of the more popular ones, more modern ones, and it's the one we used. So the view or the particular photograph that we're going to be using depends on a number of parameters. Like I said, the most important parameter is visibility, meaning if a particular pixel or piece of a building is not visible in some photograph, then of course you're not going to use that photograph. You have to determine which ones are visible. I'll talk about that in a moment, how we determine that. The orientation, if you're looking at it from the correct angle, you don't want to look at it from an oblique, too much of an oblique angle. We'll see some examples. Resolution, if you have one image which happens to be a close-up of that spot that you're about to render, you might as well use that. You'll probably get a better result than if you use something which was taken from far off and has very low effective resolution in that area. Now, it's not really rocket science. There is no real way of determining what is the best thing to do. And there's a lot of heuristics that we use here, and we mix basically these type of parameters in order to try and come up with the best possible result. So basically, it's a combination of these things. So here's an example. Let's say here's your building, and you have 3 photographs. One is taken from view 1, one is taken from view 2, and one is taken from view 3. So we have snapshots of this building from these 3 angles. And I'd like to render it now from this angle over here, the blue arrow. So I've been traveling around in space with my virtual camera, and I happen to end up at a position where I'm looking at the building from this angle over here. Now the question is, which is the best photograph from these 3 given photographs to use to texture this area over here? So that's a question which arises. So here are 3 different views, and let me tell you why each one of what would be the. Let me tell you what I have to say about each individual view. So view number 1 is probably not going to be good at all. Why is that? It's not going to be good because it's occluded. If you're looking at the building from this angle, you're probably not even going to see anything on that wall because this portion of the building is getting in the way, so that's going to be basically occluded and invisible. It's not even going to be present in that photograph. So view number 1 is going to be irrelevant. View number 3 is relatively, seems to be good because it's very close to the orientation or the camera angle at which I'm looking right now, the blue one. So it seems to be as though it would seem that the view number 3 is very close to the image that I'm going to be generating right now from the blue angle. View number 2 actually gives me something quite different. It's looking at it more or less head-on at this area of the wall on the side over there. So actually, if we look at view number 2, we're going to have a nice, clear picture of that wall. Whereas if we're looking from view 3, that wall is going to be in a very small grazing angle, and that's probably not going to give the best type of quality for that area there. On the other hand, we're not really interested in that much quality because we're looking from this angle as well. So there is a balance of the different criteria over here. So this is what we call a view which is best normal, meaning we're looking at from an angle which is very close to the normal, meaning the vector which is perpendicular to that particular polygon. We call this the closest to eye or closest to camera because it's closest in terms of camera position to, in terms of the eye viewpoint to what the camera is looking at right now. So theoretically, at least, it looks very similar. And these are the type of views which are going to be probably the most relevant. View number 1 is not going to be relevant at all because, like I said, we probably don't see anything there anyway. So here's the building that I showed you on the previous slide. So if you're looking at it from this side, then that wall there on the side is going to be taking up just a small number of pixels in the image. There's not much information over there. Whereas if you're looking at it from what we call the best normal, you're looking at it more or less head-on, and therefore we have a very nice bunch of pixels which represents that wall, and we should be able to use it. There's more information in there. Okay, so what do we actually do in practice? So here are my 6 photographs of that village the village scene that I showed you previously. So I've taken just 6, and if you look at it carefully, although it looks right now like a jumble of buildings, but if you look at it carefully, you'll see that they're quite different angles. The first thing that I do, and this is after I've registered each one of these 6 photographs with the 3D model, and I remind you I do have a 3D model. Right? The 3D model is not necessarily derived from these 6 images, but it's given from some external source. So I have to have this 3D polygonal model no matter what. Otherwise, I'm going to get those flat things that you saw before, and I'm not going to be able to basically do anything interesting. So here are my 6 photographs. I register each one of the 6 with that 3D model. Basically, I overlay it, determining the viewpoint from which this was taken. Let me just tell you about the scene. There's basically a village square over here, up there as well, and there's roads leading towards this village square, and that's more or less where we're going to be looking. Now, once I have a correspondence, or once I've basically registered the 3D model with a photograph, I can then build what we call a depth map. Meaning what? Meaning that I render the 3D model from the angle from which each of these 6 photographs was taken, and I look at the Z buffer. Right, this is the Z buffer. Right, what you see here is basically a visualization of the Z buffer, meaning the dark areas are closer to the camera and the light areas are further away from the camera. And basically it gives you a depth map of each of these different photographs. That I can get only by rendering the 3D model. If I do not have that 3D model, I cannot render these 6 pictures. So I render these 6 pictures by basically just doing a simple polygonal rendering and stealing the Z buffer, grabbing the Z buffer. So I grab the Z buffer, I have 6 of these now, and I keep them for future reference. Future reference meaning that I'm going to be using them when I'm doing the rendering. So I need to have these. The reason I need to have these is to determine the occlusion. Right, so to be able to determine for each individual pixel in the new image that I'm trying to generate, which of the corresponding or hopefully corresponding pixels in these 6 photographs are actually visible, meaning they actually represent the correct piece of the surface in space that I'm looking at. Okay, so this is very similar to what is done with shadow mapping. For those of you familiar with the rendering process in which shadows are generated, there are 2 families of algorithms. The first family is what they call shadow maps, which are very simple algorithms, and they're based on this type of concept, meaning build some sort of depth map from the viewpoint of the light, right? So the shadow is cast by a light. So typically the way you simulate that in the rendering process is you build a shadow map from the angle from which the light is looking. And then you use that to do all sorts of visibility calculations and then get the shadowing as you're rendering. The other family of shadow algorithms is shadow volumes. It's a completely different technique, and it's unrelated to what I'm showing over here. So this is very similar to shadow mapping. Those of you familiar with the technique will see that it's basically identical. And basically the way shadow mapping is done is by taking the point that you're trying to render and transforming it backwards in the direction that the shadow map was taken from. Basically, the direction meaning one of these 6 directions over here. And once I have that, I can then compare the height in the Z buffer to the height. Sorry, I compare the height in the Z buffer to the height in these maps, and by doing a simple comparison, I can then know whether that point is visible or not. So that's typical shadow mapping, and it works here as well, and that enables me to determine the visibility. And that's basically what this slide is all about. I'm sure most of you are familiar with it, so I won't get into the gory details. So it allows me to determine a per pixel visibility very efficiently. Okay, so let me tell you a little bit about GPUs. This is a slide that I stole off the NVIDIA website. A GPU is basically a processor which sits inside the computer next to the CPU and allows you to dedicate a lot of processing power to graphics computations. So it doesn't take up any of your CPU. It works, as you can see in this nice little graphic over here. Instead of having just a single CPU where everything goes through, including the graphics, you have a separate processor for the graphics, and all the green guys, which are the graphics operations, go through him and don't clog up the CPU, and that gives you a boost in performance. That's the whole idea of GPUs. And like I said before, it allows me to do 2 things. It allows me to intercept the graphics pipeline because I can actually program this GPU, whereas previously In the more traditional architectures, you're not able to intervene in the graphics pipeline. All you can do is send down textured polygons, and that's the end of the story. You can't really do anything different from that. And it not only does it allow you to intervene and to intercept the graphics pipeline, it also allows you to actually program it to do very specific things that you might want to do. And in our case, we're doing what the standard way of doing it is to write things called shaders. Shaders are little segments of code which tell you how to operate on two different pieces of data. So one piece of data is the geometric data which you get through vertices, the transformations and stuff. And the second piece of data is related to the scan conversion or the image generation at the end, the pixels, and that's what we call a fragment shader. So you can actually build two different types of little programs, one which does some sort of geometric manipulation, and one which does some sort of rasterization type of operation. And we need actually both of these types of shaders in order to do what I described earlier. Right, so we use GLSL. This is just to scare you or to convince you that we're actually writing real code. And this is not just a pretend scene. So this is the type of code that we have in the Vertex Shader part of it. All sorts of, those of you familiar with GLSL, some of this might be familiar, you might recognize some of these type of things. It's pretty standard operations. This is the type of code you see in those type of shaders. That's what we have in our Vertex Shader, in our Fragment Shader. We have a number of other things. I'm not going to get into any of the details. That's just to flash some code at you. And here I want to show you some results. So let me tell you what you're seeing over here. Basically what you saw previously. Here we have our three-dimensional model of the village. Right, the lines, which I'm not sure you can really see, but there's blue lines here overlaid on the buildings. That's the geometry or the coordinates and the polygons of the actual scene. And these are the same 6 photographs that were taken previously. And what I'm going to do now is I'm going to fly around this scene with a virtual camera, so you'll be seeing the viewpoint changing all the time. And what I want to do is to be able to get the correct rendering of the scene based on this 3D model and these 6 reference images, where again, as I showed you before, I've built a depth map for each one of them individually. I've stored that in the system, and that's what I use to do the actual rendering by determining which of the 6 at every given point in time is visible at every given pixel, and then determining among those visible which is the best to use or which combination of those is the best to use. So this is it, basically. Now, what are you seeing over here? It's not running as smoothly as it should, for some reason. This was taped off the screen of our computer where we have the software installed. What you see over here is the result. This is the rendered image at every given point in time as the camera is moving around. Right? And it looks pretty reasonable. Now, what you see over here, and this is quite interesting, is a color coding of the pixels. We have here 6 different colors, right? So there's red, green, blue, and some other. There's 6 different colors over here, and each pixel is colored according to one of the 6 photographs which contributed to that pixel, right? So that's the game we're playing over here. And notice that it changes all the time. Some changes more, some changes less. In this particular rendering, I have 3 different renderings which I'm going to show you. In this particular rendering, it changes less. Why is that? Because in this rendering, we're choosing let me run it again. In this particular rendering, we're choosing the photograph with which to texture a given pixel. We're choosing the photograph which had the normal, which was closest, which is the best normal in terms of the direction that you're looking at that polygon where the pixel happens to be. And this is actually the closest to static texture mapping. Right? So if you're trying to think of static texture mapping as a special case of multi-texture mapping, this is actually the closest you can get to it. Because typically when you cut out a piece of a photograph to use as a texture, you usually cut out the piece of the photograph which is looking straight on at that particular wall. So it has the best normal view. So here I haven't done this offline ahead of time, but I'm doing it on the fly, but the effect is very similar because in the end I end up choosing a very similar pixel as I would have used had I done the texture mapping in the traditional way. So you can see that well, stop. You can see that if you look, for example, over here, you see that the front of this building is textured using photograph, which is coded by the light blue, and that stays more or less that way all the time. Even if I'm moving around, the front of that building is still going to be textured by the same bunch of pixels right over here. And that's because I'm choosing the, sorry. That's because I'm choosing over here what we call the normal view. Now, let me run the result of what you would. Now, this is using the view which happens to be, per pixel we're using the photograph or the view which happens to be closest to the camera viewpoint, most similar to the camera viewpoint. Right, so you can see that, you see these massive changes, meaning that we're almost flipping from one photograph to another depending on the viewpoint. When we get with our virtual camera close to the angle from which a particular photograph was taken, then massively a lot of the scene is textured using that particular photograph. And as I move on to another viewpoint, which happens to be close to one of the other photographs, again we get that wash of the entire scene using that photograph. But it's not collective. You can see that even though the mass here, or it's dominated by the blue one, there are still patches where I'm rendering using one of the other photographs. Now let me point out as well, you have some black pieces over here. The black piece means, guess what? The black piece means, let me run it again. If you want to know what the black piece means, have a look over here. I hope you can see it. So for example, here's a black piece down here. It corresponds to this black thing over here. There's a hole in the image. That means that that specific piece of the geometry is not visible from any of the photographs. So basically we have a complete occlusion, a complete black hole. None of the photographs covers that portion of the geometry. Therefore, we can do whatever we want, but we're not going to be able to get the correct information. So there is a challenge here to be able to fill this in. I'll talk about that in a moment, but you can see that there are many holes in the data set. So even though we have 6 photographs which more or less cover the data, cover the scene, it's still not complete, it's not perfect, and there still are pieces which are missing.
Why is it jumpy?
I don't know why it's jumpy. It really shouldn't be. Yeah, on my machine here it's running rather smoothly. I don't know why it's jumpy. It shouldn't be. Okay, so that was what happens when we use that particular criterion. And here's a combined version, meaning in this particular rendering over here, we're using a criteria for choosing the pixels, which is a combination of the normal criteria and the best viewpoint, or the closest viewpoint criteria. So you can see things are quite dynamic over here. Right, so the same area of the image, for example, this house over here, at some points will be textured, at some angles will be textured from one photograph, at some angles will be textured from a different photograph. Sometimes the same piece of the geometry, what we called previously the same polygon, will be textured half from one photograph and half from another photograph, all different combinations of the two. So actually we're not committing to anything in advance in terms of the texturing. Everything has been done on the fly as we're rendering, and hopefully we're getting the best possible result because we're taking the best possible texture pixels and using them at every given point in time. We still have these holes over here because there are still areas which are not entirely covered. Yeah?
As the view moves around, it looks like it just jumps from one text to the other. Would it be feasible to like phase in, to blend?
You could, yes, you could. Yeah, you're right. You're saying that over here it's red and then suddenly it's all going to jump to blue or something like that, right?
On the left, you can see suddenly some of the building faces change to like a brighter image or a darker image.
Yeah, so you could. We're not doing any blending. The reason we're not doing blending is that sometimes it blurs the image. If the registration is not 100% on, then if you have, let's say, even a 1 or 2 pixel miss between the two photographs, then and when you do the blending or averaging between the two photographs, you're going to be blurring if you don't have 100% accurate registration. So in some cases, it makes more sense not to blend the data. It's just sharper that way, even though you might get a slight mismatch and discontinuities, which are not really visible. It's probably more desirable than having blurred imagery as a result of not such good registration. But if you have 100% registration, you could try what you...
I think the Vertex original blending, but I think he hand registered everything also. So I think that helped a lot.
Okay, so those are the type of results we're getting. Just wanted to show you a few static snapshots from those videos just to point out, just to show you, to compare a couple of the things over here. This is the real photograph. In other words, what you're seeing here in this particular comparison is I've taken a new photograph, not one of those 6, but a new photograph. This was actually from some real video sequences those 6 were taken from. So I basically have an entire sequence, which I chose not to use, but I chose just to use 6 of the photographs. But I have an entire sequence. And I took one picture from the sequence, which is basically this one over here. This is a real photograph from not one of those 6 angles. And this is what the rendering technique produced, which is supposed to be supposedly close to this one over here. So you can judge for yourself how close it is and how real it looks. It's pretty good. There's some places which I've circled which are worthy of closer attention, in which there are slight differences. Let me point out over here. In the real photograph, there's some bricks. You see these? Over here, you should be able to see some stacks of bricks. Well, they are not over here. There are no stacks of bricks up here. The reason being is that the 3D model that I had of the scene did not have any stacks of bricks in it. And therefore, it's basically lost when I do this synthetic rendering. There's all other types of artifacts that you get here and there. You can see that this structure in the village square is slightly bent. Sorry, over here it's slightly smeared on the ground because some of the registration was 100% good, and there's some artifacts also in the 3D model. So that's those two. Here again is the real photograph, and this is what you get if you do eye rendering, meaning you're using the photograph which is closest to that. And look at the bricks again. The bricks are there. So this is the real photograph with the bricks, and in the synthetic photograph, or the one that I've generated on the fly, we have stacks of bricks, but they look sort of bent over. The reason that I have those stacks of bricks is that I'm actually using a photograph which is quite close to this one. Therefore, those bricks are in there, but since I don't have the real 3D geometry, they're not going to be rendered quite correctly, and they're basically swaying over. And this is just a comparison of the 2 synthetic images. There's no real one over here. Basically, you've seen these before, but now they're just side by side. So there's various artifacts that you have in one and you don't have in the other, and so on and so forth. You can see for yourself. So what are our conclusions so far? This is work in progress. We're still working on improving it. The rendering quality is definitely improved relative to just static or simple texture mapping, the traditional way of doing things. It's certainly more convenient. You don't have to actually sit down and per each image polygon, each scene polygon, go in there and cut out from some photograph a texture map and do the texture coordinate UV mapping, which sometimes is quite a pain. It's very time consuming, so it's much easier to do. The only thing that you really have to do properly is that registration of the 3D with the photograph. If you're doing that manually, meaning you don't have any real data from your camera, navigational data, that might be a little bit painful. But hopefully when you're out there doing this for real with a real camera, you will have navigational information, meaning 6 degrees of freedom, and then it's very, very easy. You're able to get real-time performance thanks to using the GPU properly. One thing we did come up against, and I think this is more of a technical issue, we're working on resolving it right now, is the number of texture maps that we can use right now using our relatively simple rendering software is limited. We're using up to 8 photographs, 8 of those pictures like you saw. And that's because of some technical issues we're having with programming this stuff, but I don't think it's a real limitation, because in terms of actual texture memory, you can pack in much more than that. So that's a limitation we have right now, which I think will go away as we proceed. And something which I think is certainly it's important, and I think it's also quite possible if you're using this type of rendering technique versus the traditional texture mapping, is being able to fill in those black holes. Right? So there's always going to be a couple of pixels where you're missing data for, because these pixels happen to not be covered in any of the photographs. And we're looking into ways of filling in that missing texture information using something called inpainting. Inpainting means taking the information that you have around it and somehow interpolating or extrapolating it inside that black hole. And I think that using this particular way of rendering will make this easier than just regular texture mapping. Right, so is this really practical? Not really practical. Why is that? Because there still is one main problem here, and that is the geometry. We still have to model very precisely all those polygons of all those houses in that village. Right, photographs are easy to get. You just go out there with your camera, snap, 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 record the viewing parameters, and you're in business. So you have the photographs are easy to acquire. But how do you acquire a good 3D model of the Knesset, or of that village, or of any other urban scene, right? To actually generate a good quality polygonal model requires a lot of work, and that's basically the main bottleneck in any modeling process, and even in this as well. So how do you make that go away? Well, using this technique, if you're doing texture mapping the way that I described it here, as opposed to the traditional polygonal texture mapping, single texture mapping thing, you could probably make that go away. We haven't done that, and that's something we're trying to think about right now. The idea being, instead of using polygons, you'd use what we call point clouds. And point clouds are very easy to obtain because there's no real structure to them. There's no edges of polygons which all fit together properly. Point clouds are something that you can obtain using your scanning device. So you have these large industrial grade scanners, and you can go out with them into the streets. You basically point it at the buildings, and you shoot laser beams, and it comes back with points in space. And that way you acquire very large quantities of points in space. And you don't really know or care where these points belong to. Does it belong to this polygon? Does it belong to that polygon? Does it belong to the roof? Does it belong to the wall? Just a bunch of points in space. All you have to do is then to align your photographs with these bunches of points in space, and you can use exactly the same rendering technique that I described here to render that data set. So this rendering technique is amenable to a much easier way of modeling the 3D geometry, and I think that'll probably be the future way of doing things, because it's very easily done in practice by just taking out the scanning device and basically pointing and shooting. So here you see a couple of examples. These are not my examples. It comes off this site over here. This is a company which does this for a living. It's called 3dlasermapping.com. And basically what you see here is point clouds, or colored point clouds, of these two scenes. Here it's some castle, I guess, in England, and here it's a couple of houses from a village. So there's no polygons over here. It's basically just points which have been colored using some sort of texturing technique. And you can see it looks a bit crude because the rendering technique is not very good, what they've done over here. And there's no real surfaces in terms of polygons and so on. It's just bunches of points all over the place. So it looks kind of pointy. It doesn't really look very clean. It's very noisy. But I think this is the way to go. If you do the rendering properly, then the fact that you have points which are easy to acquire as opposed to polygons which are not very easy to acquire and to set up, then I think life will be much simpler, and it'll be relatively painless to be able to do these type of to enable these type of applications. So that's a future type of direction. We haven't done anything about it. Right now we're working on polygonal data, which we get basically from people who do that for a living as well. And there's companies out there which produce polygonal 3D data, and they expend a lot of effort into doing this, and it's a very expensive process as a result. This would be much cheaper and much more effective and much easier, basically. So basically, that's what I have to tell you. If you need more details, you can go to this website, and there's some stuff over there. Thank you.
Just remember, for more questions, that you leave any confidential information for after the video is done. Do you have any questions?
Have you thought about using stereo techniques to get the geometry? You've got a lot of views there.
Right, so the question is, have we thought of using stereo techniques to acquire the geometry? That's exactly how the geometry is acquired. People who acquire the 3D polygonal data on a commercial scale, they actually do that. They take pairs of photographs, stereo pairs, and they have a special machine called a stereo plotter, I think. And people sit there and look at it, and they sort of turn these dials, and the point moves up and down in some virtual space. And that way they actually measure the heights of points. And then they have software which supports all this, and they're able to use that to actually construct the polygonal forms of the data set.
So it isn't automatic.
So it isn't automatic at all. There are, of course, you probably know that in computer vision, people are trying to do geometry extraction using stereo automatically all the time, with very limited success so far. So first of all, it takes a lot of time, computing time, I mean, and the results are so-so. They're not very good because there is a big issue there of correspondence, meaning if you have a stereo pair, you need to be able to tell which pixel here matches which pixel there. And basically, that gives you afterwards the height. So with a manual process, it's a person who actually does the matching, and therefore that problem goes away at the expense of more human time involved. So it's not automatic, but the results are better. So stereo, or sort of stereo, is what is used to produce those three-dimensional data sets. Yes?
This is if any movements in your data sources will cause a lot of havoc in your actual mapping. For example, if your light source changes, if you have a car moving down a street, that sort of thing. Any particular thoughts on how you handle moving?
Right, so we haven't really done much about dynamic scene. So the question was, what happens if the scene is dynamic, if cars are moving, cars are driving, and people are walking, and that one photograph is taken at one point in time, another photograph is taken at another point in time. You might have the same car in two different photographs at different positions because in the meantime it's moved from one place to another. And in fact you do, in this example over here, oops, you're not going to see it because they're too small, but there are two photographs over here in which you have the same car in two different positions because the car had driven, and in one photograph it was taken at one point in time, and then later on at a different point in time and also a different point in space because it had driven. So you'll see the same car in two different positions. We haven't dealt with that problem at all. So what I've described over here is certainly good for static scenes. For dynamic scenes, it's a whole different ballgame. But those type of things can and will happen. Yes.
The polygonal model is only used for generating shadow maps and not doing
The polygonal model is used for generating the So the question was, what is the polygonal model used for? Why do we actually need it? Why is it so important? No, it's used for two things. It's used for generating the shadow maps, which then allows me to do to determine the occlusions. But it's also used for the actual perspective computations as we're rendering. I think we're done. Thank you.
Thank you.